Hello all, let's begin with Chapter 6 Chemical Kinetics. In this video, we will cover till rate law. Chemical kinetics is a branch of chemistry that deals with the study of rates of chemical reactions, factors which affect the rates and mechanism of chemical reactions. Let us first study about rate of reaction. It is defined as the change in concentration of any one of the reactant or products per unit time. Rate of reaction is of two types, average rate and instantaneous rate. Let us begin with average rate of a chemical reaction. Average rate of a chemical reaction is change in concentration of a reactant or a product divided by the time interval during which the change occurs. Average rate is equal to change in concentration of a species upon change in time, which is equal to delta C by delta T. The average rate of a reaction can be either positive or negative. Positive when the rate of concentration of the product increases and negative when the rate of concentration of the reactant decreases. Let us consider a reaction A gives B. Average rate of consumption of A is given as minus of delta A upon dt upon delta T, and average rate of formation of B is given as plus delta B by delta T. Average rate of reaction is given as minus delta A upon delta T, which is equal to plus delta B by delta T. The unit of rate is given as mole per decimeter cube per second. Let us study instantaneous rate of reaction. The rate of reaction at any instant of time is called instantaneous rate of reaction. If dx represents small change in concentration of any chemical species during the small change of time dt, then the instantaneous rate of chemical reaction is given as rate of reaction is equal to dx by dt. This is the graphical representation for determination of instantaneous rate. In this figure 6.1, a tangent drawn to the curves at time t1 gives the rate of reaction. The slope thus obtained gives the instantaneous rate of the reaction at time t1. The instantaneous rate dc by dt is represented by replacing delta, that is triangle, by derivative dc by dt in the expression of the average rate. In chemical kinetics, we are concerned with instantaneous rates. Let us consider a reaction A to give B. Instantaneous rate of consumption of A is given as minus dA by dt. Rate of formation of B is given as plus dB by dt. Instantaneous rate of reaction is given as minus dA by dt, which is equal to plus dB by dt. For 1 mole of A and B, rate of consumption of A is equal to rate of formation of B. Consider another reaction where A reacts with 3B to give 2C. Stoichiometric coefficients of all the three species are different. So we write, and the rate of reaction is given as minus dA by dt equals to minus of 1 by 3 dB by dt, which is equal to half dC by dt. This is because a rate of consumption of B is 3 times the rate of consumption of A and rate of formation of C is twice the rate of consumption of A. If we consider any general reaction like this, where A moles of A reacts with B moles of B to give C moles of C and D moles of D, then the rate is given like this. Let us now study how the rate of reaction and reactant concentrations are related. The rate of reaction at a given temperature for a given time instant depends on concentration of the reactant. Such rate concentration relation is the rate law. To explain rate law, we'll consider an hypothetical reaction. This one. Rate of reaction at a given time is directly proportional to the molar concentration at that time raised to simple powers. That is, rate is directly proportional to the molar concentration of A to the power x into molar concentration of B to the power y. This can also be written as rate equals to K, which is a rate constant, into molar concentration of A to the power x into molar concentration of B to the power y. The sum of the power of exponents x and y are determined experimentally. They may or may not be equal to the stoichiometric coefficients A and B. K is the proportionality constant known as rate constant, and equation 2 is a differential rate law which is determined experimentally. Now if exponents x and y appearing in the rate law tells us how concentration change affects the rate of reaction. For x equals to y and which is equal to 1, then rate equals to K into molar concentration of A into molar concentration of B. The rate of reaction would be doubled if either of the concentration of A and B is doubled. For x equals to 2 and y equals to 1, then rate equals to K into square of the molar concentration of A into molar concentration of B. Third, if A is doubled keeping B as same, then rate increases by a factor of 4. Third, if x equal to 0, the rate is independent of A. And fourth, if x is lesser than 0, the rate decreases, molar concentration of A increases. Now we'll see about writing the rate law. For this, consider a reaction. Twice of H2O2 gives twice of water and oxygen. For this, the rate law is given as a rate equals to K into H2O2 molar concentration. Similar way, now try this question. Now in this, the rate of reaction is experimentally found to be proportional to the square of the concentration of NO2 and independent that of carbon monoxide. Write the rate law. Rate equals to K into NO2 square into carbon monoxide concentration. Therefore, rate equals to K into NO2 square. This way, we can write the rate law for different reactions. Hope you have understood the concept. Thank you for watching the video.